Hi everybody, my name is Josh. I'm from Terminal.com, and I'm going to be talking about terminal and high-performance workloads and a little bit of everything today. But I work at Terminal. We work on the fastest secure Linux cloud. So what is Terminal? We work on high-performance computing in the cloud. And when I say cloud, I really just mean distributed systems, and I'll talk about that a little bit more. So these are the people that made Terminal. Varun is a Stanford PhD. He used to work at Google as a data scientist for a couple of years and wanted to make a distributed system sort of similar to the Borg, but with virtualization. And so I'll show you a little bit of what that looks like in a second, but that's sort of the goal from a high-level view. So Terminal works on high-performance clouds. We deal with distributed systems problems, so like system discovery, application discovery, service discovery, all that kind of stuff. And we're trying to make everything function a little bit faster. And I will show you guys what that means in just a second. So terminals are full Linux boxes. They behave exactly as your machine would in your lap. That includes being able to basically close the lid on your machine and open it back up and come back at the same state. And we call that snapshotting. Terminals are very, very fast because it is container-based technology. The overhead is extremely low. And we believe that we're about 2% in the CPU and about 2% in memory. And so it is very, very thin. It's essentially like running a bare metal server. We use snapshots, which you might be familiar with from VMware. These basically allow you to capture a computer or a system running at a moment in time. And that includes the disk state, the RAM state, and the CPU cache. So you basically have everything just as if you were closing a laptop on your computer. We also have a really good security profile, which I'll talk about a little bit more later, but that includes the ability to upgrade the kernel of the machine without disrupting the application. And that comes as a primitive based on our ability to teleport workloads, which I'll show in a second. So Terminal is a different thing than a hypervisor and a container. So hypervisors are secure and powerful, but they're not particularly quick. They have very long boot up times, and they're quite large. Docker containers are a really good answer for this, but they're insecure, they don't have live migration, and they're missing a lot of enterprise features. And Terminal attempts to be the best combination of the hypervisor and the container. And you can also run Docker containers inside of Terminal as well, if that's a thing that you want. Yeah. So this is a quick comparison table showing what you get with Terminal versus VMware and Docker. I think the cloud is a really important one. I know there's definitely a lot of efforts there, but it's quite hard to stand up a service on Docker right now. And you can actually use Terminal as a platform as a service to run Docker if that's a thing that you're interested in doing. And it's different qualitatively than Amazon because Amazon is running 1 VM per container, and that's a different model than what we think you should do. There's clustered storage, which I'll talk a little bit about in this presentation, but I won't cover too much today. That's basically a distributed block-level file system. We deal with live migration, which I'll demonstrate today. It starts up very fast because it's a container. It's compact because it's a container. We have snapshots, and it's quite secure. So how Terminal fits in. You can run all this stuff, Docker, RPMs, tarballs, whatever you want. We have automatic networking where all the machines that a user has automatically talk to each other. And if you need to expose them, then we have an API for doing that. And everything provisions in seconds, and it uses a distributed storage layer that we built. So who uses Terminal? We launched our public cloud in December, and we have a lot of users on there. You guys can sign up as well just by going to terminal.com. And Crunchbase and Code Academy also use Terminal as well. So let me show you guys a demo. So I'm going to go to terminal.com. And here's terminal.com. I'm going to go and make a new snapshot. And I'm going to get a CentOS box. And this is going to have 2 CPUs, a quarter gig of RAM, and 10 gigs of disk. And we're going to start this up. And so it's going to take a couple seconds. And what this is doing is it's getting the, basically we've committed the state of the CentOS box to disk. And we're going to restore it, including the RAM state, into memory. And so this is going to restore RAM. It's going to take a few seconds. And then we should have a running box. And we built a web ID so that you can interact with it just from your web browser. You actually don't need to go to SSH. But all these boxes have full SSH, and you can, of course, just use that. So here we have a full CentOS box running. And you can see I have top. And one of the things that I always want in a server that I can't get very easily is the ability to resize it. It'd be really great if I could just like press a button and get something like 6.4 gigs of RAM. And so that's what I'm going to do on here. And you'll see that I have 6.4 gigs of RAM provisioned. And then I'm going to go back down. So that's an interesting thing. There's a lot of technology that goes into making that work. And what actually happened there is that we live migrated from one physical box to another. and the application is not conscious of that change. That includes the IP address, the CPU cache, the RAM cache, the disk state, everything is migrated over. And so we can also do this with things like Spark. So Spark is an Apache Hadoop-like thing.
So this is running bare metal?
This is running bare metal. It can also run in a hypervisor.
Okay, but I mean, when you say you literally migrated it to
Yep.
another.
It moved from one physical piece of metal to another physical piece of metal. And it did that without a hypervisor. So now I'm going to grab Spark. So Spark is an Apache product. We're going to boot this up with 2 CPUs and 3.2 gigs of RAM and 10 gigs of disk. This is going to take a little bit longer to come up, and I don't really want to wait for it, so I've got well, I guess we can. But I've got it running here as well in a different box, but we'll wait for this one to come up. So this is going to restore RAM state, and this includes the entire Crunchbase data set. And so that's just in memory as soon as you boot the machine up with Spark running. You have all the dependencies necessary to get Spark going. There's a bunch of different snaps that I'll show on here as well. But basically, this allows you to take a piece of software and ship it, not just with the dependencies and the different things required for startup, but actually to ship it with a running state. And that is qualitatively different. So I'm going to do a quick count so you can see that this is Spark. We did a count of the 68,000 items in there. This is hosted on a port, which is 4041. So if I go to -4041, which is how we access ports, you'll see that this is running Spark. And so this is just an entire Spark installation. It's a complete cluster up and running in one click. And that is what we do at Terminal. So I'm going to go back and show you guys a little bit more of the presentation, but that is the entirety of the demo that I wanted to show today.
What do you actually do when you provision?
We are spinning up the RAM snapshot from the disk back into memory. And so the amount of time it takes is basically the time that it takes to read the RAM, read from disk into RAM. And so that's what's happening. What we've done is committed machine state to disk like a file, and then you conversion it. So you start with CentOS, and then you take a snapshot after you've done a few things on it, and then you have a different version of that CentOS machine. And you can think of it basically like a branch-based file system.
So you give people space on a bare metal box.
Yep.
And then you give them some amount of memory.
Yep.
And read data from disk into memory.
Yep. So this is a quick recap of the thing I just did. This just shows you a fast version of the spin up. And so then you have a running server. And then here's a quick version of the resize that I just did. All right. So let's talk a little bit about the technology that makes this possible. So we work on containers. Containers are basically the way that we control processes in Linux. And we did not use LXC or libcontainer. We did our own custom container implementation. It's the terminal container implementation. We can run Docker inside of our container implementation. The same is not true of Docker being able to run terminal. As you saw, there's very, very fast resizing and almost no overhead on the product. And it has automatic snapshotting. So you can cause snapshots to occur basically every 5 minutes. Or if you want to do it, you can even do it on every diff in the file system, but that gets to be a bit network intensive.
Does this have custom, like a custom kernel module?
Yeah, so we do custom kernel modules, but we can run, it's a couple patches, and so we can run other people's kernels as well. So we have software-defined networking. As you saw, we're able to migrate the IP address from one physical box to another physical box, and we do it so fast that the application is not actually aware that a change has occurred. All user machines automatically talk to each other, and you can expose access to these machines programmatically as well. Teleport is the feature that I just demonstrated, which is the live resizing. You can live migrate across physical hosts. When you teleport, everything goes with you, and because of this, you can apply kernel security patches without rebooting. So essentially what you're doing is migrating from one piece of metal to another piece of metal without changing the application state, upgrading the kernel, and then migrating back. Or you could just migrate to a box that already has an upgraded kernel. That's another option as well. So in summary of the tech, there's secure containers, we have very fast networking as you saw, and teleportation. So we're solving a lot of hard technical problems for distributed systems. This also works on high performance computing systems which tend to be diskless and with networked file systems. Because our distributed file system is implemented at the block level, you are able to put things like ZFS or network file systems on top of it pretty easily.
What do you do for security?
For security, we are patching everything. We can run AppArmor or SE Linux if necessary, but not everybody wants that. We basically have the ability to apply kernel patches without rebooting, and so that's a primitive that nobody else has. And so most of the time, you're not really worried about your stateless systems. You're worried about the stateful things where if you take that machine down, you have a problem. And so if you could migrate it, upgrade the kernel, and then migrate it back, then you've solved that stateful reboot problem. And so I think that that's a much better security story than, for example, VMware, where you can't upgrade the kernel in the guest OS without taking the machine down. And so I think that's the difference. There isn't really any way to defend against everything, but as soon as a kernel patch comes out, we can apply it much faster than other people can. So in terms of the value proposition, we think it gives a very good computing experience. The idea that you can boot with all your dependencies and your RAM state in just seconds is a very, very powerful way of doing development and of running systems. We think it makes sense because, as I'll show you in just a second, you can actually pause these machines and then recover them. And we think that this helps you to do software much faster. So let me talk about those individually. We think being able to deploy with not only the dependencies but the RAM state makes it so that your deployments are much more reliable. I wrote a piece recently about the Knight Software fiasco, which was basically a high-speed trading firm, and they were actually doing their deployments using a USB stick, which is not particularly reasonable in the 21st century. Using Terminal, you can have a dev machine that gets to a specific state, and then push that state, not just the dependencies, directly to your production machines. And you can also iterate and test a lot faster if you have RAM snapshots. You can get a machine to a state right before it breaks and then keep going back and reverting and doing your testing. You don't have to spend a lot of time restoring to that specific state. And so it makes your development, your QA, a lot faster. The cluster is also self-balancing, self-healing, and auto-scaling because of the fact that the applications don't know that they're being teleported. We can just live rebalance the entire cluster constantly. And so we get the most optimal utilization of the cluster resources with the most overhead, so you have the best performance. So when you pause a terminal, it basically takes the RAM state and moves it to disk. And as soon as that's done, you can restore it anytime that you want. So a lot of companies have clusters that they've invested in. And one of the problems that people have is you are running a job on your cluster and somebody else with a higher job priority needs to come in and use that cluster. If you're running a several hour MapReduce job or something of that nature, then you have this problem of, do I stop this job before it gets completed? And if it's important enough, you do. With Terminal, you don't really need to think about that anymore. You just pause the job, you go run the high priority job, and then when that's done, you resume the job from the previous place that it was. And so that saves a lot of time. You're not wasting computing hours anymore. Servers also are able to, you can turn off servers, so you can migrate all of the workloads off of a server and increase the density of your resources as much as you want. I think that when I think about data science, the primary thing in my mind that's holding back data science is DevOps and not algorithms. We have lots and lots of algorithms, but deploying them and testing them quickly is quite difficult right now. It's very difficult to get your machines up and running. It's very difficult to get your test cluster up and running and restore to that state. And so if we can iterate faster on the algorithms through better DevOps, I think that that pushes the entire pursuit of data science forward very quickly. Most of the stuff that you do on Terminal is automatic. And so you don't really spend a lot of time dealing with problems that you might have previously had. So you don't have to migrate machines manually. That's just automatically taken care of for you. And you can set auto-scaling rules so that the machines just automatically change based on the load on the CPU, the memory, the network I/O, or the disk. And we think that we have a very strong security story because of our ability to hot migrate and therefore replace the kernel without taking down your stateful systems. So Terminal, I think, is the fastest way to do computing. Using Terminal, anybody can quickly run applications with strong reliability and security guarantees. If you want to go to terminal.com and sign up, it takes about a minute, and you can email me if you have any questions. I'm going to do one more demo to show you guys what pausing a machine is like and also taking a snapshot. And yeah, that's what I'm going to do now. So I've got a CentOS box running. I'm going to run top on it. And this is number 120. I'm going to go back to my terminals menu. I am going to take machine 120 and I'm going to pause it. And you'll notice that when I pause it, this $ will go to 0. So we don't bill for pause snapshots at the moment on terminal.com. That is something that we've chosen to do on our public cloud. We're basically just not charging for the storage on that machine. And if I hit go, it'll resume in just a second. And it's basically just restoring the RAM state at the moment. And you'll notice in just a second that it'll start billing, and click this. You'll see that top is still running. And so you can do that with anything. As I demonstrated just a few minutes ago, I did that with Spark, where Spark was still running. You can do that with any program. We've seen IPython Notebook, all kinds of databases. It's pretty awesome to be able to just click a button and get back to machine state. And so that's what Terminal.com does, and I'd be happy to take questions about how the technology works or whatever you guys want to talk about.
So you said there's patches for the kernel.
Mm-hmm.
Are they, I don't know, what kind of licensing are they? Have they been submitted upstream?
Yeah, getting things upstream is quite difficult at the moment. So getting things upstream is quite difficult. If you talk to OpenVZ about their experience trying to deal with containers and getting that upstream, it hasn't been easy. So we are attempting to be good citizens, but it's quite difficult.
Again, it sounds sort of like a virtualization technology,
Mm-hmm.
but, well, I mean, you're hosting stuff, so I guess I'm trying to understand how can you load an arbitrary OS on it? Can you put?
So it is Linux only because we're using the Linux kernel.
Yeah,
I mean, so I can run, here, let me show you. So in here, we've got CentOS, Ubuntu, Debian, Octave, different Ubuntu versions, Scientific Linux. You can run all this stuff, and there's a lot of different software that's also been loaded from specific versions. I think this is RStudio running on Ubuntu, if I remember. And yeah, I mean, you can run any version of Linux on here.
Can you upload it like an image that you've got running on?
We don't allow you to do that at this time, but if you're an enterprise customer, we're happy to do that. Yeah, most people tend to start from one of these 3 or 4 machines, and then they kind of branch out from there.
Where do you run it?
Where do we run it?
Which infrastructure do you run?
So we have it in 2 different data centers right now. They're SSAE 16 certified data centers, but they're just bare metal data centers.
Did you build them?
No. We're not, we've only been up and running for a few months now, so I think we're in month 4 of being operational. So we're still running inside of just a couple racks. But yeah, I mean, there's plenty of users that we can jam in there because it's container-based.
So you're renting a bare metal data center?
We generally don't talk too much about the infrastructure that we're running on, but we are running in both bare metal and in hypervisors, depending on the customer. So some customers want complete bare metal installs, and some customers want to run inside of AWS in a VPC or something like that.
You can run inside AWS?
Mm-hmm. Yeah.
How do you actually migrate? Can you tell a bit more?
Yeah, I mean,
How do you actually switch to bare metal servers so that
right.
application doesn't?
I mean, it's sort of the same way that VMware does it. You have a RAM state, and you're diffing the RAM state from one machine to the other, and then when the RAM cache is full, you move the IP address over. Obviously, that's quite difficult to do, and there's a lot of sort of secret sauce that goes into doing that. But that's how it gets done, essentially. You just diff the RAM state and then move the IP address over. So you have to implement, obviously, like some IP abstraction to be able to do that, and you have to have some RAM abstraction that allows you to do that.
So during migration, you have 2 applications, essentially. Right?
Yeah, so you're mirroring the RAM state to another machine. And the first machine stays operational until the move is completed to the second machine. So you never have a moment where you're like not in control of your box.
Do you have any latency requirements?
I mean, it won't move over until the entire RAM cache has been moved. So if the network latency is quite high, it might take a long time for the RAM cache on the other box to catch up. In general, it's sort of the same requirements with VMware, where if you're over 100 milliseconds between the machines, it's quite difficult to do. If you look at like VMware's wide area migration, it's only on data centers that are within 100 milliseconds of each other. And so generally that's somewhat limited.
But the one that you just showed was
Yeah, that's in the same rack.
in seconds.
Yeah, it's in the same rack. So it's 10 gig between the 2 servers and hopefully not too many milliseconds of time. But we can migrate across racks. It just takes a little bit longer because there's more latency on the network.
What if you're running something on more than just one rack?
Mm-hmm. Yeah, I mean, you can do it. It just takes the network time to do it. So you can do it over the WAN too. It just takes much longer latency because you're doing it over the wide area network.
I'm asking in general, if you're running something on, say, 100 CPUs,
Mm-hmm.
would you still be able to run it inside Terminal?
Yeah, absolutely. We've tested this with several thousand CPUs.
Okay, so your VMs talk to each other.
Mm-hmm. Yeah. Sorry, good.
Oh, I was going to say, what about high-speed interconnects like InfiniBand or something?
So we're doing a lot of testing with Diskless systems right now. We're working with a couple laboratories around here to do a lot of testing around that. I would say that I'm quite optimistic that we're going to work quite well with that, but I wouldn't be able to speak to specific use cases right now.
So, as you say, it's a container technology, so do you rely on like LXC or Docker? Do you rely on, you know, namespace isolation, control groups, and all that kind of stuff?
Yeah, so we used control groups, so we did our own namespace implementation.
Okay.
And we also, we did basically every place that we thought we could make things go a little bit faster, we did our own custom implementation. And that's sort of the general theme of the company.
And could you talk a little bit more about this block storage, distributed block storage?
Yeah, so we present a ephemeral block device to each container. And that ephemeral block device is the same as a hard drive. It's ext4 formatted. And when you snapshot it, then we commit it 3 times copy on write to the cluster. And so it is ephemeral and only temporary until you snapshot it. And then when you snapshot it, it's committed to the cluster with 6 nines. So we recommend automatic snapshotting for that reason if it's a workload that you care about. I mean, for a lot of stateless systems, people just want to get it back to the original state really quickly. So if the thing falls over, you just put a new version up.
Where are you guys heading with this? What's the big goal?
I think that we want to be the best place to host Linux applications. And I think that we also want to help people host Linux applications. So if you're running your own cloud, that's a thing that we'd like to help with as well. I think just in general, we want to be the place that people run high-performance Linux. Yeah, whatever kind of data science or machine learning stuff you're doing, you should run it on Terminal because it's really fast.
So by fast, you mean fast to spin up and
No, I mean like the primitives that we give you, like being able to take RAM snapshots and restore to that and do that really fast, and also the provisioning time. When you have those two things together, you can actually do development much faster.
So it's fast in human time.
Right.
You're not speaking about performance.
No, I mean it's performant as well because it's very thin virtualization, and you saw how fast the machines boot. But I mean in human time, it actually saves you many man hours to use this. Yeah, it is quite fast. I mean, you obviously saw how fast it boots up, but I think the man hours is actually much more valuable.
So one of the problems in scientific engineering computing, HPC computing, that kind of HPC computing,
Yeah.
they may be run on tens of thousands of nodes,
Mm-hmm.
and they're using MPI for communication.
Right.
And the applications, they try to write them to do some sort of its own snapshotting of data, but
Yeah.
the problem is that when hardware goes down, that you can. I'm trying to see if does this fit into the model where you can, if they migrate stuff off of nodes onto other nodes dynamically without you're running an enormous calculation that might take weeks.
Yeah, no, that is the design. If you think about what happens at Google, if you're a data scientist, is that you are working on very large jobs. They might have 10,000 nodes in them, but they might tie up those nodes for 3 hours. And if hypothetically someone with a higher job prioritization comes in and knocks you off, you just have to start that job over. And so that sort of frustration might drive you to do kernel-side checkpointing, which is what Terminal has. And so once you have kernel-side checkpointing, it doesn't really matter what application you're running. It is just treated as an abstraction that you can just move, like a file.
Well, that's kind of why I was asking.
Yeah.
How this was going to get into the kernel. I mean, so that other big data centers, like NERSC or somebody, if they eventually might use technology like this.
Yeah, I would love for them to use technology like this. I don't know that it's going to be upstreamed. That's always a contentious thing, and I don't really have the ability to speak to it.
Okay. Any other questions? Nope. Well,
Cool.
thanks.
Thank you guys very much.